Hi, for the presentation today I've chosen a problem from the curve sketching, and this would be the third installment in these type of exercises. So we are going to look at some problems a bit more unusual compared to what we have seen before. So let's go ahead and take a look at problems that include some advanced functions such as exponentials and trigonometric. Here is a problem I've chosen. This is y is equal to logarithm of natural log of sine of x. So the request is to graph this function. We want to go through the basic items here. First issue, of course, is the domain. So many of you might benefit from starting with the point plotting, just using your calculator, getting some reasonable numbers and a first approximation. So I leave that to you to do the point plotting. That's probably the best starting place for you. Domain, well, you have a logarithm. The input of logarithm is sine of x. The input of logarithm has to be a positive quantity. You cannot feed logarithm 0 or negative. At 0, a logarithm becomes minus infinity, and for negatives it's not defined. So I require that sine of x to be positive. So for what angles would sine of x be positive? You can answer this question in one of several ways. One of them is just to go back to the graph of sine of x and quickly see where it was positive and where it was negative. This is one way. So I just go ahead and draw sine of x. You remember it was a periodic function like this, and these are the important points on it. From 0 to pi, sine is positive. From pi to 2 pi, it is negative. So the solution of this in the first circle is all the x's that are between 0 and pi. We could of course continue this curve and draw another cycle of it. So from 2 pi to 3 pi, sine would be again positive, and so on. We could have gone backward as well, and from minus 2 pi to pi it is a positive quantity. So I can say x, to capture all of these things at the same time, I can say x, any number between 2 n pi and 2n plus 1 pi, whose n is an arbitrary integer. Now, to keep the problem simple for ourselves, we already noticed that our graph is going to be periodic because sine is periodic. So we might as well just focus our attention on this portion of the domain from 0 to pi, and then later on we can say the picture is going to repeat itself once again from 2 pi to 3 pi, and then from 4 pi to 5 pi, and so on. Another way of arriving at the same conclusion is to remember that in the unit circle, sine is positive in the first and second quadrant. You remember here from 0 to pi over 2, this is the first quadrant, and from pi over 2 to pi, this is the second quadrant. Sine is positive in the first and second quadrant. Now for the range, issue with the range is typically we have to wait. Here we can have some forecast. When sine comes close to 0, that is, when x itself is close to 0, logarithm is going to go to minus infinity. So we know the range of this function starts way down at minus infinity. At the other hand, when sine of x reaches its maximum, that is sine of x becomes 1, logarithm of 1 will be 0. Is that right? So that is the maximum we expect to get for this function. Sine never exceeds 1, and so the value of this function never exceeds 0. So we already suspect that the range of this function is going to be from minus infinity all the way to 0. Let's go ahead, make sure that that is a correct guess, and come back and verify this. So we have a bit of a question in our head if that is a correct conclusion. Let's keep an eye on that, and we come back and make sure that we have arrived at a correct guess. Okay, this is domain and range. How about intercepts? Well, intercepts for the y-intercept, we need to set x equal to 0. We have to do this thing carefully because we actually essentially already said that x has to be larger than 0. If you let x go too close to 0, sine of x will also be 0, and logarithm of logarithm of 0 is not defined. If you want to insist on that, logarithm of 0 is going to be minus infinity. So if you plug 0 here, your y is going to become minus infinity. You have two options to say that y-intercept doesn't exist, so that's probably the better way to go about it right now, or to say that the intercept is all the way at minus infinity. The other end would be perhaps clearer, even though it would be requiring some work. Let's go after the x-intercept. X-intercept is going to require that y is going to be 0. If you want to set y equal to 0, then you have to require that the logarithm of sine of x to be 0. Well, logarithm of what quantity is 0? That is when the input itself is 1. Well, sine of what angle is it that is equal to 1? You know that angle is going to be pi over 2, or 90 degrees. Of course, you could go ahead one whole circle and come back and add 2 pi to this. So we have other answers like 5 pi over 2 and so on. But if you want to keep our focus on range of numbers from 0 to pi, we might as well just pick the very first number and then keep in the back of our mind that the picture and all the answers are going to be periodic, so we are going to repeat everything in a period of 2 pi and obtain lots of x-intercepts here. So by now the picture that we have in our head is something like this. Suppose this is 0 and this is pi. Our picture, one cycle of it is between 0 and pi. It has an x-intercept here at pi over 2. So that's the x-intercept. Strictly speaking, there is no y-intercept, but we have this clue that when x comes close to 0, y is going to go to minus infinity. So that is telling us the story of an asymptote, or a piece of the tail of the function that is going to sit somewhere here. So when x is 0, y is minus infinity. That is indicative of an asymptote living in this fashion. Now we go ahead and investigate the concept of symmetry. Do we have any kind of symmetry? Well, let's remind ourselves what the function was. Y is equal to logarithm of sine of x. Here, if you change x to minus x, what happens is that the sign is going to become negative of what it was, and if the logarithm was defined first time around, it's not going to be defined after you change x to minus x. So our typical ideas about symmetry are not even applicable here, that you cannot have symmetry with respect to either the y-axis or symmetry with respect to origin. So we have no symmetry with respect to either y-axis, nor do we have symmetry with respect to origin. There was one other type of symmetry we talked about, and that was symmetry with respect to translation. And we have already alluded to that this function is going to be periodic. This function is periodic because the main ingredient here is the sine of x with the period being 2 pi. The period of sine is 2 pi. So whatever is happening on one section of the curve, if we move away by 2 pi, exact same thing is going to be happening. So that means that our picture, where we started with the domain from 0 to pi and skipping from pi to 2 pi, here's 2 pi, and going from 2 pi to 3 pi, whatever happens in this section of the picture is going to happen here again. So we might as well just focus our attention here, draw the picture, and just like taking a tile off of this region and moving it over here and copying it here and pasting it here will be done with the periodic nature of this. So we know it is periodic and has this type of period structure. Next, we are going to go ahead and talk about asymptotes. You have to remember the asymptotes of the logarithm. Let me just quickly refresh your memory what the logarithm itself looked like. Just logarithm of x. Logarithm of x had a graph looking like this. This is the graph of logarithm of x. This graph has a vertical asymptote at x equal to 0. Here is the asymptote. The function approaches the y-axis. So x equal to 0 is a vertical asymptote for this function. So now we have to remember that whenever the input of this function becomes 0, we are going to have same vertical asymptote. So I go ahead and set sine of x equal to 0. Solution of that, x equal to 0, pi, 2 pi, and negative of the same value. So plus or minus pi, plus or minus 2 pi, and so on, plus or minus 3 pi are the locations of vertical asymptote. So that means I have an asymptote here, thicken it up. Here's an asymptote, a copy of it, another asymptote at pi, a copy of it at 2 pi, copy of this one at 3 pi, and if you wish to continue, of course we have at here 4 pi, 5 pi, and so on. You could of course go backward as well, go to minus pi, and all of these spots you have an asymptote. So our picture is going to be sitting here, no picture in this area. There is another tile between minus pi and minus 2 pi, which I cannot draw right now. So these are our vertical asymptotes. There is no horizontal asymptote to speak of. So we move on to the next issue. So these are all vertical asymptotes. It has no horizontal asymptote. In a conventional sense, you cannot even take the limit of x going to infinity, because the function has holes in it all over the place, and it is periodic. It's not going to have, it cannot have a horizontal asymptote. Next issue is the first derivative analysis. So we go after the first derivative. So here's my function. Y is equal to the logarithm of sine of x. Yeah, let me remind you, how did you take a derivative of logarithm of some expression? You take the derivative of that expression, divide it by that expression. That was the rule of differentiation for a logarithm. So here I go ahead and say derivative of this is going to be the derivative of the input expressions, derivative of sine, divided by just that input. So that's going to be cosine of x over sine of x, or in other words, the same as the cotangent of x. That's the derivative. Now, how do we analyze this derivative? You can either analyze cosine over sine, or you can analyze cotangent, whichever is more comfortable for you. It's more than likely that cosine over sine is easier for you to handle than cotangent. At any rate, whatever works for you. So I go ahead and say, let's set y prime equal to 0. I go ahead with this. If this fraction wants to be 0, numerator should be 0 and denominator should not be 0. So that tells me cosine of x is equal to 0. Automatically sine wouldn't be 0. Solution of this, first angle at which cosine is 0 is pi over 2. Once again, we remember that our answers are going to be periodic. So I can go ahead and list some other x's as well. Let me write that down. Cosine becomes 0 at 3 pi over 2 as well. But remember, 3 pi over 2 wasn't in our domain here. It is pi over 2. 3 pi over 2 is here. Derivative might be 0, but the function didn't even exist there for the derivative to exist. So at this point, I don't have anything. So this is not in the domain of the original function. It cannot be considered for the derivative. So I passed by that. The next solution of this is going to be 5 pi over 2. 5 pi over 2 is in the middle of this block. So here's 5 pi over 2. And so on. So we suspect again we have 7 pi over 2. We don't have any use for that. And the 9 pi over 2 is midpoint here. Okay, these are the spots at which the derivative becomes 0. What is the function? What's the function value at those points? So let's go ahead and calculate logarithm of sine of, for example, pi over 2. Well, sine of pi over 2 itself is 1. Logarithm of 1 is 0. It means that this point has a coordinate 0, 1. Excuse me, let me correct myself. That point has the coordinates pi over 2 and 0. Corresponding to this, there is a point on the function that is 5 pi over 2, 0, and so on. So these are the points where the tangent line is horizontal. They are right on the x-axis themselves. These are those points. Let's go ahead and do a first derivative analysis here. Here is of the x-axis. let's just focus on from 0 to pi. Our solution was pi over 2. I put pi over 2. Our derivative y prime became cosine over sine or cotangent. Either of them, cosine over sine. Well, this is the first quadrant. Over the first quadrant, both cosine and sine are positive, so the ratio will be positive. From pi over 2 to pi, cosine is negative, sine stays positive. So that becomes negative. Here what I can say is that the function itself, y, is going to be increasing, and then it will be decreasing. So the point in between is going to be a relative maximum. This being the only thing that happens for this function, not only is this a relative maximum, but also it's an absolute maximum. What happens at the endpoints of my interval? Well, at 0 again, we remember logarithm of sine of 0. That is going to be infinity, minus infinity. At pi also, sine of pi is 0 and logarithm is going to be minus infinity. That is telling us the following, that our picture that starts from down here. Here was a tail. It's increasing all the way to this point, so it's going to come up. And then it's going to be decreasing after that. It's going to decrease in presumably in this fashion and go down. And the same tile is going to show up in any of these regions. So between 2 pi and 3 pi, I have a copy of that. And between 4 pi and 5 pi, another copy. And so on. And of course, on the negative side, there would be a copy of this thing between minus 2 pi and a pi. Now, we are done with the first derivative test. We know that the function is increasing here and decreasing there, and this is going to be therefore the relative max and of course absolute max. We are already vindicated on our guess that the range is from minus infinity to 0. Since this is the absolute max, it's obviously the case that we don't pass through 0, and the asymptotes tell us that we actually go to minus infinity. So this guess is confirmed here. The only thing is left is a second derivative test. From our first attempt, it looks like that the function is always going to be concave down, but we have to go ahead and make sure that our guess is actually correct. Perhaps there is some features here that we are missing. Maybe this function isn't behaving just in this simple way. Perhaps when it is coming up, maybe it comes up, goes through some inflection, and then keeps going up. This is a possibility. Here is a function that is increasing all the while, but its concavity is not as simple as we have assumed. We have to go and make sure that the picture, our picture, are actually talking the truth. So I need to go ahead and do a second derivative test. I cannot be sure of the answer I have as yet. So by now, we had that y prime is cotangent of x. So what is y double prime? If you remember, what's the derivative of cotangent? Well, that was minus cosecant square of x. Or if you want to start at this with more familiar functions, cosine and sine, you differentiate that, you are going to get minus 1 over sine square of x. It's the same functions. So what can we say about this y double prime? This quantity, whenever it exists, is going to be positive because I'm squaring it. And with this negative, we are going to have a second derivative that is always negative. So y double prime is always negative. Always means whenever it exists, it's negative. Of course, there were plenty of places where the second derivative did not exist because the function itself didn't exist. So wherever this expression is defined for us on the domain of our function, it is negative. That means that the function is always concave down. Y is always we could go ahead and make a table, but that would be a waste of effort. There isn't really anything to show on the table. This already is quite loud in terms of what's going to happen. It's always concave down. If it is concave down, it means our original guess was correct. This purple curve is correct, and this yellow curve wasn't something that's going to happen. So this thing doesn't happen. The function just stays concave down all the way through, and this is our guess as to what the final shape of this function going to be. Okay, so that is our final answer. We go ahead and pick another problem to do, and for that perhaps we pick something that includes exponential functions. Let's work on this one. Y is equal to exponential of 2x minus exponential of x. So here's a new problem. Okay, this has an exponential component. Well, what can we say about the domain of this function? There is no restriction for exponential. The domain of this function is the entire set of real numbers from minus infinity to plus infinity. How about the range? Well, we really need to wait for this to give a complete answer, but perhaps we can make some guesses. Exponential of 2x. You remember how the graph of exponential looks like. It's a graph of, say, exponential of x. Now, if you double the exponent, you are going to go up faster. Also, it's going to decay faster. So exponential of 2x minus exponential of x looks like there's a big gap between them, that the gap keeps increasing. The size of that gap gets, the size of that gap gets bigger and bigger. If this gap getting bigger and bigger, it means this difference is going to go to infinity. So our guess is that on the positive side, the range pulls itself all the way to infinity. On the negative side, well, e to the 2x minus e to the x is going to be some negative number. It perhaps gets bigger and bigger for a while, and then later on they both converge to the same point. Both of them go towards 0. So the question is, what's the maximum gap between these two functions? We don't know what that one is, so we have to go ahead and use the calculus to figure out what the lowest value is. So we have a question to answer, which only can be answered using calculus. Next, we have the issue of intercepts. Let's go ahead and answer that. What are the intercepts of this function? If I set x equal to 0, y will be exponential of 2 times 0 minus exponential of 0. That is 1, and that is 1, and I get 0. So the function passes through origin. It's not a big surprise. We notice that both of these two functions have the same y-intercept over there, so when you subtract them, the difference passes through origin. What if I set y equal to 0? In that case, I'm looking for any other points of intersection of these two graphs. I already see that there is no such intersection, but let's go investigate. Exponential of 2x minus exponential of x, I have to set this thing equal to 0. How do I handle this function, this equation? Well, in this case, we can just be simple and factor an exponential of x. We will be left with exponential of x minus 1. Now we know that exponential of x never becomes 0. This quantity is never 0. How about this one? If I have exponential of x minus 1 equal to 0, that tells me exponential of x is equal to 1, or x itself is equal to 0. So we really didn't get anything new. We just confirmed that when y is equal to 0, x is also equal to 0. So the only intercept that we have, both x and y intercepts, are right at the origin. So here are the list of our intercepts. The only thing that we have is 0, 0. The fewer answer of these types we have, the less of a clue we are going to have as to what the graph actually looks like. So we hope that we'll get something later on. How about symmetry? Well, if you change x to minus x, the expression that you get has nothing to do with what you are starting with. Essentially, the right side of this function and the left side of this function do not look like each other all that much, and we have no symmetry. Obviously, no symmetry across the y-axis, no symmetry across the origin, and so we might as well just go ahead and mention that there is no symmetry here for us to work with. How about the asymptotes? Well, let's again go back to this exponential of x and exponential of 2x. What we notice is that when x goes to minus infinity, both of these two functions go towards 0. So the difference obviously also goes to 0. And that tells us that since the two functions originally had a common asymptote, that is inherited by their difference. So here we mentioned the following. If you take the limit of this function, exponential of 2x minus exponential of x, as x goes to minus infinity, these two individually go to 0, and so is their difference. Difference surely goes to 0. So we have a horizontal asymptote on the left hand side, and that is the x-axis itself. Equation of the asymptote is y equal to 0, or x-axis, we emphasize this asymptote is happening on the left. What else can we say when we are approaching the asymptote? Exponential of x and exponential of 2x differ in their magnitude. All the way on the left, this blue is staying above this purple. So the difference is going to be negative. That tells us what we expect is a picture like this. We are approaching the asymptote from below. Okay? If this argument was not understood, just do an experimentation with your calculator, with your basic calculator, I should say. Put some numbers, large negative numbers like minus 10, minus 100, or something like that. Minus 10 would be fine. It's going to give you a negative number. So that tells us we are approaching the asymptote. Let me write this down. We approach x-axis from below. Okay. As x goes to minus infinity, that's the picture. Remember, already we discovered that we have a passage through the origin. So we expect we are coming from minus infinity, somewhere we dip, and then we pass through the origin, and then we are going to accelerate and go up. So that's our first guess for the graph. We could of course arrive at this by some point plotting as well. Let's go ahead and check to see that our guess is correct. If our guess is correct, we have to find a minimum somewhere around here, and it looks like that we are going to have an inflection point somewhere around here. Let's see if our guesses are correct. We start with y is equal to exponential of 2x minus exponential of x. What I'm going to do now is the first derivative test. Or let me consider first derivative analysis. So y prime, derivative of this one is 2 exponential of 2x, and well, that one, the derivative is just itself. Derivative is always defined. The only critical points are where the derivative is equal to 0, so I set this thing equal to 0. I do it as I did before. I factor exponential of x. I'll be left with 2 exponential of x minus 1 equal to 0. As we said, exponential of x itself never becomes 0, and the burden is on the shoulder of the other factor. So I set this one equal to 0. That tells me 2 exponential of x is equal to 1, or exponential of x is equal to half, or x is equal to a logarithm of 1/2. Well, another way of writing logarithm of 1/2 is to write it as minus logarithm of 2. That is our critical point. Minus logarithm of 2. That is going to give us, if you wish, you find approximate value of this thing, something about maybe minus 0.7 for your graphing purposes. That is where we expect the critical point to show up. That's the indication of the location of this dip. Let's go ahead and make sure that we are correct in our assumption that we are descending up to this point and ascending after that. How do we make sure of that? We make a table. Here's the x-axis. Starts from minus infinity to plus infinity. We only have one point to worry about. That's minus logarithm of 2. Here is my derivative, which was 2 exponential of 2x minus exponential of x. Now this kind of testing will require a calculator or very good knowledge of your pre-calculus. Either way, most of the problems here can be done actually without the use of any calculator at all, but if you wish to use a calculator, that's fine. Okay, what number is it that sits here? I pick a number. I have a comfortable number in 0 itself. That doesn't require any calculator for me. If I plug a 0 here, I have 2 exponential of 0 minus exponential of 0. That is 2 minus 1. That is 1. And the sign here is positive. On this side, I'll have a harder time with using a friendly number. But I can pick any number I wish, so long as it's sitting here. Say I pick minus 10. I talk it out like this. Exponential of minus 10 is a small number, but exponential of minus 20 is much, much smaller, even if I double it up. So you can take minus 10 and plug it in this and make sure that you do it correctly, and you'll see that the difference is negative. What does that tell me about the function itself? That the function is decreasing here and increasing there. So I can say interval of decrease is from minus infinity to minus logarithm of 2. Interval of increase is from minus logarithm of 2 all the way to infinity. We have a relative as well as an absolute minimum at x equals minus logarithm of 2. If I want to make sure that I have the y value, let's see, how was y defined? Y was exponential of 2x minus exponential of x. So I just take this and plug it in my expression y is equal to exponential of 2 logarithm of 2 minus exponential of logarithm of 2. If you remember your pre-calculus, you will go ahead and actually clean this up. How do you clean it up? You write it exponential of logarithm of 2 squared, and this is just exponential of logarithm of 2. Exponential of logarithm of 2, exponential and logarithm cancel each other out. So what, excuse me, I made a mistake here. Let me correct myself. This was minus logarithm of 2, so I have negative in all of these places. Exponential of logarithm of 2 is 2. Exponential of minus logarithm of 2 is going to be 1/2. So this is going to be 1/2 squared, and that is just 1/2. So 1/4 minus 1/2, and that is just minus 1/4. So what we have is the following: x is minus logarithm of 2, y is minus 1/4. So what we know now is that this point is sitting at minus logarithm of 2 and minus 1/4. What else do we harvest here? If this is the absolute and relative minimum, well, then our range is going to start from minus 1/4 and go all the way to infinity. So we got the answer to missing part here. Starting point of our range turned out to be minus 1/4. That's as low as we go, minus 1/4, and then we go up. Okay, this is as much as we could get out of the first derivative test. The second issue is the second derivative test. Obviously, we are expecting to get an inflection point. We have to work to get that. It looks like, if there's nothing else happening, that the function is concave down up to here and concave up after that. That's our guess right now. We have to go ahead and make sure our guess is correct. Okay, so next issue is second derivative test. Excuse me, second derivative analysis. Second derivative test is an expression used for something closely related, but not exactly this. So our function, you remember, was exponential of 2x minus exponential of x. The derivative was 2 exponential of 2x minus exponential of x. Second derivative, I'm sure you can quickly get that. Second derivative is 4 exponential of 2x minus exponential of x. Set this thing equal to 0 to find the points where the inflection changes. Solve it just as before. Exponential of x times 4 exponential of x minus 1, setting that equal to 0. Only this component can give us a root. Set that equal to 0. That tells me exponential of x is equal to 1/4. I solve it for x. X becomes logarithm of 1/4. And when I clean it up, it's minus logarithm of 4. You can still use rules of logarithm. Since 4 is 2 squared, power can be brought up outside. Minus 2 logarithm of 2. Leaving it like that would have been fine also, but this is nice because it shows us a relative magnitude of this compared to the other answer we had. You remember the other one was minus logarithm of 2. What we find out is that location of the intercept is twice as far as the absolute minimum itself. Now we can go ahead and make our table. We have the x-axis from minus infinity to plus infinity. We have just one point on this thing to worry about, is minus 2 logarithm of 2, or if you wish, minus logarithm of 4. and that expression was y double prime is 4 exponential of 2x minus exponential of x. Again, you can choose a test point such as 0, plug it in this expression, and then you see you get positive, and you get a large negative number and plug it here. This is almost minus 1.4. So if you take a large negative with a similar reasoning as before, you'll see, or just use your calculator, that this is negative. So what we can say is that the function y itself is concave down, is concave up here. So concave down on interval from minus infinity to minus 2 logarithm of 2, concave up on minus 2 logarithm of 2 all the way through infinity. So what we have so far is that if we go as far as this point, minus 2 logarithm of 2 that's where the inflection changes. From minus infinity to this point is down, from that point onward it is up. All that is left to figure out is the y coordinate of this point, and then we'll be done with this problem. So we go ahead and figure out where is the inflection point. X of it is minus 2 logarithm of 2, or if you wish, minus logarithm of 4, either way. How about y? You remember y was exponential of 2x minus exponential of x. So y will be exponential of, so I can put minus 4 here. Actually, it becomes minus 2 logarithm of 4, and here is exponential of minus logarithm of 4. Just as before, exponential of logarithm of 4 is 4. 4 raised to the power of minus 2 is 1 over 16, and this one is going to be 1 over 4. You subtract these two by taking common denominator, and you'll have 1 minus 4, that's going to be minus 3. So inflection point is at minus 2 logarithm of 2 and minus 3/16. So that concludes the solution of this problem. Okay, we have solved two problems somewhat different from all the rational functions and radicals that we had before. We got a bit of taste of sine and cosine, logarithm and exponential. You go ahead and try a few more of these functions. Good luck and God bless.